so here we go. Here's going to be class homework number 9. Yes, homework number 9, problem 1. And so we have a Hue Heart Dynamics lab experiment here where we have this block on a slope, and it weighs 4 pounds, and at state 1 it is running down there at 5.8 feet per second. That seems very specific. At 35 degrees is the angle, and the kinetic coefficient of friction is 0.2. And at the bottom of the slope there's this spring, and the spring is kind of held boingy at in place by some rope. Its original length would be, or its unstretched length would be 2 feet long. It's got a spring constant of 50 pounds per foot. And that plate and that rope are constraining it, so it's only 1.5 feet, right? So it's already got math, 0.5 feet pre-squished. At point A, okay, so this is where it's located at this instant. It's this value A is equal to 3 feet. So it's going to hit the spring. It's going to compress the spring even further. It's going to pause, and then it's going to release and go back up, right? And we want to figure out how far up the slope it's going to go, right? So I'm trying to pick out a hard problem and figure out what the efficiency of this is going to be. So I think I'm going to be able to do this without screwing it up the first time, but I picked a pretty hard problem. So here I wrote everything down. What we want to do, part of the thing that we're going to know is that there's going to be friction all the way along, and we don't know how far this is going to be compressed. So this is kind of the thought process that we have to go through, or some of the things we have to recognize right away. This is going to slide down, it's going to compress it, and then it's going to be released and it's going to slide back, right? So what we really need to do is figure out how much is this going to compress that spring. And this adds to a complication because we don't know the entire length that it has moved. So let's go ahead, and we could do this in multiple stages, but I think we only really need to do it in 3 stages. This first state, right, when it gets and presses the spring all the way back down, and then when it stops again at the top. I think that's what we're going to have to find, right? But that's okay. We'll just draw the thing out. So it's best to do this with sketches, and sometimes I'll try to modify the sketch. But I think because we have 3 stress states, or not stress states, we have 3 states onto this thing, it might be worth writing them out. So I'll draw them this way right here. I'll start out here. So here's what this thing looks like. Oh, by the way, I like to have this little hash mark, so I meant to put all those all the way up here to show that that's the ground. Okay, so I'm going to draw it up here. This is where it's starting. So this is going to be state 1. I said stages, but I meant states. Here's state 1 right there. Here's going to be state 2. So we'll draw with the spring kind of compressed a little bit. So he's boingy right there, right? And I like to draw it as a dashed line right here, but I guess that's fine, right? So this is going to be state 2 right there, right? So I guess I'll draw this thing up a little bit right here. So one thing that we're going to know here is this is going to be the del at 2 right there, right? Where it's actually the additional amount of displacement. Okay, this is also going to be, there's also going to be the distance this thing is going to move is going to be that A. So the total amount of movement it's going to make between states 1 and state 2 is going to be A plus this del 2. I have to be careful. This del 2 is an additional displacement. It already has some amount of displacement, being the distance between, the difference between the unstretched length and 1.5, right? Well, let's just get to that point, right? And then we can maybe make another diagram of where it's going to come back up. And actually, maybe I could draw it back up in here. If I left enough room, it would have been helped, right? So We know it's going to have some losses, so it's actually going to come up. Now, I want to make another diagram. I'll make another diagram. Should have planned this all out, shouldn't I? Anyway. So we're going to say our main equation, KE plus PE, the kinetic energy plus the potential energy plus external work that's going on, is KE2 plus PE2. So we'll start out with the initial kinetic energy, and it's 1/2 mv1 squared. Okay, and that's going. We told it was 4 pounds, so make sure that we include that 32.2 when we go to do the mass, and we were told that it's going at 5.8 squared. Full disclosure, I picked a problem and it had whose solution was 5.8 and worked backwards, and that's why it's such a specific number. But this is not what the thing was asking. Alright, so we're going to have 2.089 foot-pounds of energy, kinetic energy. Now the potential energy, here's one of the first things that we're going to have to deal with here. It's got some potential energy at this original state 1. That's going to be based on 1/2 del 1 squared, where del 1 is going to be LO minus B. And we could do that in our heads. It's 2 feet minus 1.5 feet, or 0.5 feet. Right? That's the initial thing. But it's also going to be, and this gets a little confusing right here. Let's see, we're going to use this from. Alright, I'm trying not to make a mess here of my drawing, but like this right here is going to that corner. We also have this corner right here. So here is the height change between here and here. Let's see, let's write that out as, let's call that delta y 1, 2. Right, delta y 1, 2. That's coming through there. We're also going to have, and maybe I could change these up right here, 1 and 2 right in there. We're also going to have this distance that this thing has moved. I meant to, maybe I'll write that out. It's this right here. And I'll write it as delta S 1, 2. So I'll say that delta S 1 to 2 is going to be equal to A plus del 2. Other things I'm writing over to the side, delta y 1, 2 is delta S 1, 2 times the sine of theta. Yes. So when we get to this potential energy is going to be the start, and down here is going to be the datum for this one. And so that's going to be the weight of the thing, or mg, times delta y1, 2. And one of the things we're going to need to know in order to be able to do this, this is an unknown, because we don't know how much this is going to be compressed. Right? So that's going to add to the complication here. So let me go ahead and put in here the stuff I do know. And this is going to be 50, and this is 0.5 squared, right? So that's, yeah, that's the difference right there. Plus the weight of this thing, which is 4 pounds, and the delta y, which is going to be A, which is 3 feet, plus, I guess I'm going to put del 2 right in there, times the sine of 35 degrees. So So I could get this. This is actually not the hard one. The hard one is going to be the potential energy at state 2. We're going to have to do a little bit of extra stuff, but we'll just get through it. We're just walking through the thing. No, not that big of a deal. So we got 50 times 0.5 squared divided by 2. Okay. That's 6.25. Maybe I'll write that right there. 6.25. I'll give myself some more space for the next line. And then we're going to have 12 times 35, right? 4 times 3, 12 times 35. Does that mean sine of 35? Right, so that's going to be 6.88. Is that right? Yeah, I guess so. Yeah, 6.883. So we're going to add that together. Boom. So we get a constant of 13.13. That's good enough. And plus, now we're going to have 4 times del times the sine. So just 4 times the sine of 35. Boom. So we're going to have 2.294 del 2. All right. Now we're going to get the work that's going to take place. All right. So there's going to be friction, and maybe I should have done the free body diagram up here. We'll do the FBD up here in this little space here, because we should have done this originally. Maybe that's the first thing I should have done, but we'll fix it by putting it up here. FBD, and here's the normal force, Fn, and here is the weight. The weight, and now the friction force is coming this way. At least on the way down it's going that way. On the way back up it's going to go the other direction. And here's your FBD right in there. And all right, the sum of the forces, and this, I guess this is the x prime and y prime. The sum of the forces in the y prime direction equals 0. And we'll go that direction is positive. And just Fn minus, and this is our theta right there, minus the weight times the cosine of theta equals 0. So we can write, this is terrible, I'm trying to squeeze too much in here, but Fn, I've already written out all this stuff right here. Fn is going to be 4 pounds times the cosine of 35, and therefore equal to 4 times, actually I think we just solved for that. No, we did cosine. Boom, we get 3.277 pounds. Right. So coming down to here, when we go to the external work, it's all going to be from U1 to 2 is going to be negative friction times delta S1 to 2. Right, which is going to be the A plus that guy right there. So we know that's going to be coefficient of friction times the normal force times A plus del 2. So let's put some values into there. So negative 0.2 times the 3.277 times our, what did we say A was 3 feet, and plus del 2, which we don't know. Right? So there was del 2 we don't know, and there's still del 2 we don't know. I said this was a complicated problem. Did I leave anything out? I don't think so. So 0.2 times, whoops, we already had that, boom, there we go, 0.2 times that is 0.6553, and then multiply by another 3. Right, so we're going to have a negative 1.966 plus, and oh no, make it minus, sorry, minus. That's going to be in front of del 2, so that's, I should have kept that in there. 3.277, boom. So that's 0.6554 del 2. All right. Now, when it gets to the bottom and it pauses, woohoo, we got something at least is a little easy. It pauses, that means the kinetic energy when it gets to state 2 is 0. Great. The potential energy, unfortunately, well, this is going to be at the datum, so that's good. Right, that makes it a little easier to have to deal with. Anytime I said my last name in like one of my classes, anytime I said deal, everybody would laugh. Deal with it, right? Because that's my last name. Maybe that's funny. I don't think so. 1/2 K times del 1 plus del 2 squared, right? So that's going to be equal to 1/2 times 50 times del 1, which we know is 0.5, plus del 2, which we don't know. And notice that it's the quantity squared. Right? So, gotta have to do that little FOIL thing, aren't we? We're going to multiply both of them by 25, but it's going to be 0.5 squared times 25. So we're going to get this equal to 6.250. The next one, the outside and inside, is going to be 2 times 0.5 times del, right? So we're going to have plus, there's also going to be times 25, right? Because there's 25 right here, but we have 0.5 times this twice, so 2, so just del 2 times 25. So we end up with 25. I hope you could follow that. And then we're going to end up with plus this squared times 25. So 25.00 del 2 squared. Ooh, ugly. All right. No, don't worry about it. We'll be able to forget it. All right. So we're going to have all of these things, and we're going to plug them back into here. So let's write them out. K1 is going to be 2.089. Great. So we had that up above, right? And then PE1 is going to be plus 13.13, and this is really the thing that drives everybody, but we also have this amount of 2.294 del 2, right? And now we have the work that's happening on here, so this is the losses, so it's going to be minus 1.966 minus 0.655. Is that a 4? I can't read that. I think it's a 4. Make your 4s look like 4s. I believe that's I think it's a 4. Let's double check. Let's just double check. All right, 3.277 times 0.2. Yeah, it's got to be a 4. That's a 4. And times del 2. It's going to be equal to 0. Woohoo! At least one thing that was easy. 6.25. A little concerned by that, looking at this, but that's okay. Hopefully, this is not going to become an irrational number or imaginary number. 25.00 del 2 plus 25.00 del 2 squared. Collect all those things together. Let's see. Let's collect all the constants. Let's put them all onto the right-hand side. So we're going to have equals 0. 0 equals, and on the right-hand side, I'll just start out with this. I'm going to 2.089 plus 13.13. I'm going to do them on the left-hand side, then make them negative. That's really what I'm doing. And I'm going to subtract out 1.966 due to friction. And then I'm also going to subtract out the 6.25. Boom. Right? So now I'm going to bring them over to the right-hand side. Makes me nervous, but it's going to have to go. It's going to have to be a negative number. Negative 7.003. Right, so put them over on the right-hand side. Now let's go all the ones that are del's, and we're going to put those on the right-hand side. So we start out with 2.294 minus 0.6554. Right there. And that's going to be minus 25. Right, but then we're going to take it as negative, so it ends up being positive. Positive 23.36. Is that right? I think so. And then finally, plus 25 del 2 squared. This is supposed to be del 2. Now, we have a quadratic. What do? We find the quadratic equation. If you don't remember that, because maybe you've been taught all these years to just plug it into your calculator, I think the educational system has let you down. I just called it squared when I meant to. But that's going to be, ready? Negative b plus or minus the square root of b squared minus 4ac divided by 2a. If you have no idea what I just wrote down right there, I weep. But that's all right. What we're going to do is, like, this is A, this is B, and this is C, and we plug them in there. So it's going to be negative 23.36 plus or minus the square root of B squared, which is 23.36 squared, minus 4 times A, which is 25.00, times negative 7.003. Now that's good. We had the negative and the negative. It's going to make a positive underneath the square root. So that makes life good because we don't have to worry about this going into becoming an imaginary number, or a complex number, I guess you would say. This is imaginary. This part of it imaginary. And I have 2 and 25.00. So let's figure out the roots of this. Of course, you could just put this into a root finder, but I think you kind of get rid of, like, some of the thought process. Maybe, I don't know. Is that true? Maybe. So let's see. I'll square that number. Take 25 times 4. Actually, I could do that in my head. I should actually do this in my head. 0.003. Duh. So we add those together and take the square root. I actually like to do this in stages right here. So I like to do this. So I go negative 23.36 plus or minus, and what I got underneath the square root was a 35.30, and then we're also dividing this by 50. So what I find that I would from this, if we take 23.3 and if we do the subtracted one, that's going to give us a negative number, which doesn't make any sense, so we just throw that one away, right? But now if we do the add of these, which ends up being subtracted, we end up getting a crazy number. That's not true. What did I do wrong? 35.30 and 23.36, subtract it out, divide it by 50. Yes. So this is the additional amount, 0.2388 feet, or negative, we'll write it down for the hell of it, 35.30, and I'm going to divide by 50. We'll get a negative 1.173 feet. Makes no sense, right? But now we know how far this thing has compressed, the additional amount this thing has gone down. So we're able to bring this to the top of the page. This is page 2. I'll fill out the rest of the stuff later. Now we know how far it has gone down. Oh, not this is problem 1. Continue. Dot, dot, dot. We figured how far it went down. So it went down a delta S1 to 2 equal to, let's see, A plus, it'd be A plus delta, right? A plus delta 2. So it's going to be 3 feet plus 0.2388 or 3.2388 feet. Yeah, easy enough. I did that in my head. Okay, so that means we're going to try to figure out how far it slides. Now, what we want to do is maybe draw this out again to try to explain, so you can see, and hopefully you're getting some amount of understanding out of this, that it's going to start here at state 2, and I'm going to kind of draw this out. Oops. So right here. At state 2, and it's going to slide back up, and it's going to stop somewhere at state 3. Right, and let's keep this guy in here. And here, I think as my variable, I might use, okay, so this is going to be my del 2. And this right up here is going to be my del, how do I want to write this? I think I want to write it as del S23, but I got to be careful. I think that we don't. We have to remember, because down over here, I defined my del S1 to 2 as all the way through that it went, right? So we're actually finding from this edge upwards as opposed to from the very bottom. That's what's giving me kind of pause in terms of like the way I decide to arrange the thing. But yeah, I could fill out other things on here as I need to go through. So I have my let me write out the equations. Sorry, the main equation we have right here is going to be KE2 plus PE2 plus work done between 2 and 3 is equal to KE3 plus PE3. Okay, so a lot of this is already kind of, no, we have to do some things. Okay, so KE2 is equal to 0. PE2 was stuff we kind of wrote out, but we don't have a value for it, right? So we have this equation we can put in our del 2 for it. It might be easier just to write out this one again, right? So let me write out that it's 1/2 K times my del 1 plus del 2 squared, right? Because that's going to be equal to 1 times 50 times my del 1 was 0.5 plus my del that I found, 0.2388. The whole thing squared. And so I actually find a value. All right, so let and take 0.5 and add it to that, what I found before, and square it and multiply it by 50 divided by 2. I could have just done by 25. And I find that I get 13.65, and these are foot-pounds, by the way. All right, so that's the energy it has stored in the spring. Now it's going to come upwards a certain amount. We don't know how far yet, so that's the thing. Up, this is between 2 and 3, but it's going to go that far right there. So I'm going to say that it's going to go negative friction, right? So it's still going in the opposite direction. So the friction, the normal force hasn't changed, so the friction force is still going to be the same. And let's see, I'm trying to think of the friction on the distance right there is going to be, oops, sorry, del 2 plus delta 2 to 3. That's the thing I'm trying to get. We got to also remember that we have to, I guess I didn't have enough room. I kind of moved it over to the side too much. KFN del 2 plus delta S 2 to 3, and then we stuck in this minus 0.2 times Fn, which we got is 3.277, and then a del 2, which we know to be 0.2388, and then plus my delta S 2 to 3. So I might as well get the actual values for this where I can. 3.277, 0.2 times, and 0.2388 times. So this is going to be a negative, not a lot, right? 0.1565, and then a negative, and that's the same thing. I should have just stored that somewhere because I've written that down several times now. It's the 0.6554. Delta S 2 to 3. All right. Now the good news at state 3, the more good news, right, is that KE3 is equal to 0. The bad news is that PE3 is actually going to be, and this is going to be a little funny here, is actually, it's for one of the things, the spring's going to bounce back, but only to where that rope will let it. So we actually are going to have that 6.25. We can actually recycle that because that's going to be at state 3, right? That's like probably going to be one of those ones that like go, oh, you might have missed it. I think it's kind of tricky. But now we're going to have plus. Now we have to have, and we have to go from the datum. We have to go from this datum right here. So it's going to be the del 2, right? So we have to use that. So we have to use this del 2. But now it's going to be, let me draw it up onto here. It's going to be, depends on what we used. What did we use? I guess we did use the bottom corner here. So I'll try to make that clear by drawing a line that kind of goes that way to there. It goes to right there. And we're going to go delta y 2 to 3. Which isn't going to be exactly consistent with what we were using before, but it'll have to do. So we're going to have the weight of the thing times our delta y 2 to 3. Right? So we just need to be careful here. This one, I'm just going to stick the number. I'm going to leave this for the ride because we need to write out some more equation part stuff. We've got the w, and it's going to be del 2 plus delta S 2 to 3, that whole thing, times the sine of theta. Yes, I think. This one we can just put in the number 6.25 because it's going to be the spring returning. You have the weight of 4. Here, this is going to be the what we found, 0.2388 plus the thing we want to find. Darn, I'm kind of cramming it in here. Times the sine of 35, right? Sure. Alright, so we're going to have some constants, so I'm going to put those together. It's going to be 4 times 0.2388 times the sine of 35. And we're going to add that to 6.25. Boom. So we have 6.798 plus 4 times sine of 35, or 2.294 times delta S23. At least this one's not going to be a quadratic, right? So let me stretch this up. And we plug this back up into the equation that we know. And we're going to go, we got 0, that's great, plus 13.65, 13.65, great, minus 0.1565, probably seems worth it, or a small amount, minus 0.6554 delta S 2 to 3 equals 0 plus 6.798 right there plus 2.294 delta S 2 to 3. And let me see here. We're going to take our 13.65 and we're going to subtract out 0.1563. Boom. We're going to subtract out 6.798. Great. Okay, so that's over on this side. And I get 6.696. It's going to be equal to, and we're going to add that to there. So take 2.294 and add 0.6554, add them together. 2.949 delta S 2 to 3 and delta S 2 to 3 is going to be equal to, wait for it, 2.270 feet. There you go. Let me think about that. Well, these were originally only 3 feet apart. It went down, compressed, and came back up. It didn't make it back up to 3 feet. So that really right there is the thing that we would be comparing to, right? Because I've laid this out so that it is comparable to A. I can write this out. Now, if you want to say, well, what's the efficiency of this right here? It's not that hard to do. Take a look at state 1 versus state 3. What do we have going on here at state 1? Well, we have spring efficiency right here. Do I want to say that? Yeah. And we have this. Okay, yep. So we have the spring amount of energy, but we also have this potential energy taking place right here. But this del actually is going to be recouped back over here, right? The 6.25 is still in here, 6.25. And then, is that going to be, I'm trying to think. Yeah, I think so. All right. And then here's the energy at the end. Yep, okay. So if we're gonna do an efficiency, this is going to be energy out divided by energy in, right? Or so we have is that gonna be right? Yeah. Do I want to do it this way? This has been really long. Is anybody going to make it to the end of this thing? Ooh, 40 minutes. No, we were. I don't think anyone's going to listen to this whole thing. That's right. We'll be fast forwarding through it. All right, energy out is going to be the final energy divided by the initial energy. So we'll write that the energy out is going to be 6.798 plus 2.294 times our 2.270. Alright, and so now our energy in is going to be our potential energy, or we need the potential energy and kinetic energy, right? So we need to have all of the energy that it started out at state 1. So it's going to be this potential energy and the kinetic energy together. So let's write those in there. So that's going to be, I should write this as an equation, but I didn't. So too bad. The kinetic energy isn't actually that much compared to the potential. We're going to have 13.13 plus 2.294 times del 2, which we found to be 0.2388. We probably could have messed around with this in another way, but this is the way I decided to do it on the fly. 6.798 and 2.294 times 2.270. Add them together. I get like 12.01 foot-pounds. That's how much it ends up with at the very end, because there's no kinetic energy. But starting out, we had 2.089, 13.13, and then the 2.2, is that a 94 or 49? No, 2.294. But they look a lot alike, but they're not related to the, okay. I think so. Yeah. 0.2388 times, wasn't much, and then plus. Let me get 15.77. So my efficiency of this whole thing is going to be, divide that out, 76.14%. So here are my answers. I'm going to say that I'm going to have delta S is going to be equal to 2.27 feet. Boy, do I want to write it that way? I might. It's how I want to express it. Do I want to express it from the wall? Like I should have asked how far up the slope. What I'm answering from is from this line right here. And maybe I'll cheat and, okay, this is called A right here. Let's call that B. I don't think the original problem said that, did it? The original problem didn't give me a spot. I should probably have called that B. Would have been a good thing. So, but I'm going to write up from B. See, and that will tell me what the thing. And then B is I'm going to have an efficiency of 76.1%. And we have a very, very long video, very, very long problem. So if you waited to the last minute to start transcribing the video, you would have been disappointed. Hopefully you understand the whole process here. This is a solvable problem. And I have students that would do this, just so you know. I mean, this semester, I don't think many of the students will be doing this on their own, but I had a lot of students that will do this on their own, and a lot of students that will really be frustrated by it. But now that we have the video's solution of the thing, unfortunately, we'll have a lot of people that are transcribing it. But I do want you to go through and be able to solve a problem like this. I can't ask this problem on an exam. I mean, I could, but I'm not gonna. It's just too long of a problem. But it is doable. It just takes some determination and some understanding of the nuances of what's taking place. So I wrote the problem. I like the problem, so I'm going to keep it. 45 minutes later, though.